So, welcome. Well, welcome to this big and noisy room with me. I might be making noise with my voice from time to time. That's out of habit. My name is Patrice. Roy is not my first name, it's my last name. And I work at Université Sherbrooke and at Collège Jean-Leroux, a college where I come from, around Montreal, around the Montreal area. Who am I now? Some of you might know me already. Those who don't, I have a few kids. I have a few animals. I used to do flight simulator software before I started teaching, but that was a while ago because I've been teaching for about 18 years now. And what else? Yeah, I work a lot with the games people, which led me to this talk, to be honest, because the games people, they hate exceptions with a passion, some of them at least, and some of them, and they're not alone. Some of you, I guess, in the room do that too. I don't hate exceptions, as you'll see, but I can understand the concerns. So we have a strange situation in C++ where we kind of depend on this mechanism that is both very useful and lacks love. It needs more love these days. So what am I planning to do today with you? Since I'm involved with SG14, where we're studying alternatives to exceptions for those who don't like them, and since I'm working also at the ISO C++ Standards Committee, where we care about that thing, and since I'm also working at the WG23 ISO group, which is interested in security and robust software, I'm kind of concerned by all this. So the costs of exceptions, the reasons why we use them, the reasons, what we understand or not about it. So this is not a pro or con exception talk. I'm going to try to see how it works, what it does, what it doesn't, what are the alternatives, what are the costs, in terms of speed, but also in terms of, because I have numbers, but I don't know if I'll have the time to show them. I'll make them available to you guys. In terms of programming effort also. And maybe if I have the time, a few dirty tricks, because exceptions are funny sometimes if you're a creative person. And there might be things I show you that you won't want to bring back to your office, which is okay, you'll keep them with you as a gift. Okay. So when I wrote this proposal for a talk, this is essentially what I wrote. So if you read that, that's why you're here right now. So this says exceptions are part of C++ right now. I don't think they're going away. I really doubt it. They might change. They might change. We might have quality of implementation issues right now. They might not be fast enough for some purposes. There are segments of the community that don't want it, but since it's not going away, we have to find ways to make it work better for these. We have to work on the interface between the exception-aware and exception-blind code. So there's work going on, and SG14 is part of the effort. Then exceptions let you focus on the meaningful. They take the effort involved with error handling away from the core of your code where you're concentrating on the real stuff and bring it to a location where you can actually manage it and think about it separately. Otherwise, they tend to pollute the code. So that's in itself something interesting. It helps you program, reason, and debug. And they're not meant to occur very often. I mean, they're meant to be exceptional. That's the reason for their name. If they occur often, you're not using the right error handling mechanism. There are others. Okay? So the idea behind that thing is that when you go to the try block, it's expected to be relatively fast. It might be faster. Maybe it should. And when you're going to the catch block, you kind of assume it's going to be slow, but you don't mind because it's not supposed to happen. And when it happens, well, you have things to do. And some people think when you're using exceptions, you should try and catch. In fact, you rarely do. You shouldn't. That's the whole point. You shouldn't care about it unless you really have something to do. I'll try to have examples of that later on today. That's my goal, at least. So what you can see here is essentially what I just said. There are concerns. There are people who don't like them. There are people who don't like exceptions because they bring an alternative control path to your code, and they think it makes the code more difficult to reason about. I wouldn't go that far. I don't think that's true, but I think that there's some education to be done about that, and it's not being done. So there's an effort in terms of explaining to people how to handle that thing. That has to be done. It's done in the books, but some people don't read them. So it's not for exceptions today. It's not against exceptions. I use them, I'm honest, and I understand the needs of those who don't. It's a matter of perspective, knowing what the alternatives are and what it means for you. Okay? So here's where we go. This is the basic example I use when I teach exceptions myself to those who have not programmed much. So it's a very naive example, but I think it shows well what you have to do if you don't use them and what are the options. The example is naive, but the problem isn't. So it's a matter of integral division, where if you divide by 0, of course, the world is going to collapse into a black hole and you will disappear along with your family, as everybody knows. The basic signature is what you have there. So the basic interface, which is much more deep, because Lisa gave a tremendous talk about that yesterday. Very, very insightful. This is very naive. And you expect to pass a numerator and a denominator and get the quotient as output. Okay? It's that simple. So I'm calling that the natural interface, but it's like a pun. You know, the basic interface is something much more complex. And you of course, you have to wonder if you pass something wrong to that function, what will happen? As I said, the black hole will occur and you will die, but past that, I mean, you expect to have something more insightful to do in such cases, because dying, well, it might not be your first option. You could say it's a precondition. I think it's Andrei Kreminski, I don't know if I pronounce his name properly. He had a few texts on the internet a few years ago stating that when you write the precondition, if people break it, it's their damn fault. They should have checked before. It's their effort. Contracts could help. There's a number of things you could help from the outside, but if you're saying it's a precondition and somebody passes 0 anyway, well, get what they deserve, no? For some people, that's not satisfying, but it's a reasonable approach. And somebody who takes that stance, we have to say that it's a valid way of dealing with the thing, for some domains at least. This is the wrong way to do things, but it's the one you see a lot, especially in other programming languages where they're taught that when you catch an exception, what you show is you print the stack trace and then you leave. And you let the program in an incorrect state and continues running with wrong values. So hiding exceptions is not good, and letting the problem continue is not good either, because in this case, you're screaming, ah, something bad's going on, you know? And then you still die because you haven't reacted, which is pointless, really. But to be honest, I work with many companies. I teach with professionals, students, undergrads, grads, and this is what I see most, which terrifies me, to be honest. But I do recognize that teaching error handling practices is not being done, and if it is, it's not being done right. And I haven't seen in my life a real solid course on that topic, which I should probably put up. There's other solutions. You could actually crash voluntarily, and some people do that. The games people, that's probably what they would like to do. They prefer, if something bad happens, to crash, recover, and go ahead. Because they don't really care. They're not going to kill anybody if something fails. They're going to lose customers if something goes bad. So what they want is a quick crash, say I'm sorry, and restart. So terminate is fair. Assert is probably fair, especially when you're debugging your code, because otherwise you might be in trouble. Abort, terminate, exit, whatever. So something that says something went really wrong and let's quit it. Let's hope it doesn't ship as such, but somebody whose application domain allows this could make this into a valid way of treating the problem. It's not treating the problem, but at least the program is not continuing with wrong data. This is another one. It's a bit radical, you know, die! There's an assert and you die. Why not? And at least you have a message outputting, I guess. So it's another way of doing things. And from the outside, well, the interface is respected. And you're calling the function. You have nothing special to do. And normally it works. And if it doesn't work, well, you're dead. But you accept that. But that's OK. As long as it's something you accept, it's part of your mental contract, it's OK. It's fair. So people who do that, I can't find fault with it as long as their domain is not self-driving cars or airplanes. This is another way to do it. It's very C-ish, but it's not invalid. I mean, lots of APIs do that, or things to that effect, meaning that if you have an API that uses C-like stuff, COM, for example, or others, you can throw exceptions. So you're going to add arguments either as return value simulated because you're going to return status codes, or you're going to put a status code as an argument. It's equivalent. So this is valid. You see that. It works. I mean, you do your tests. You return some arbitrary value in this case because you don't really care, because people should be checking the status before doing anything. Meaningful, fair, OK. As long as they check, because the problem in this case is they might not. But Go works like this. It returns stuff that you can ignore. It works. C works like this. It's been working for a long while. So it's not bad. It's ugly. In terms of style, the problem is you have to change your interface and make it look like something else than what it is. No? You're adding an argument that has no bearing on the semantics of what you're trying to convey. So you're stuck with something that is awkward. It's not wrong, it works. But you feel dirty when you do that, and you need to go take a shower. It's true. It's true. But it does work. It has been proven to work in many cases. I mean, we have operating systems that rely on those techniques and that work. That's OK. And the other way to do this is to return the status code. I use the bool in this case, but normally it's more complex than that, some enum or whatever. And you get your return value as an argument. That's what COM does. It uses a pointer because it's C, but it's the same thing. So if you look at this, well, you, again, have a valid program where you check the result from your function, and should the result be OK, and then you take the argument. Otherwise, you know the argument not to be making sense anyway, and you're still supposed to do that. So it's programmer discipline. It gives ugly code. But we cannot say it doesn't work. It's a valid approach, and people who don't like exceptions, they can do that. And they're going to write more client code. Sorry. That's what's going on with these. You're going to write more code. You're going to do validation all over the place. But it doesn't mean your code won't work, and it's valid. This is cool, too. I mean, this is essentially what Go does. It's language supported, but it's OK. I mean, they're returning two values. You can return a pair. One of them is the fact that it worked or not. And the other one is the result. It's clean. The interface is OK. By the way, you look at the interface, you pass the arguments you expect, and you get the result with some additional information. It doesn't cost much. Really, it really doesn't cost much with respect to what you would do normally. And the code is actually quite cute. I mean, you take it like this. You check the first part, which is your result, say. And if it's OK, then you take the second one. It's actually more beautiful, I think, more pretty than the latter two. I don't know what you think, but it seems better. It looks better to me, at least. More functional, maybe. It preserves the arguments to their natural state, natural being what we expect for them to be. And this is C++ 17 code, which is actually pretty cool, too. I mean, you can destructure your return statement into two variables that are actually located within your if statement. This is where they live. They die after that. So you get both the OK state and the result state from a single return. They are decomposed in two variables. And then you can check one of them, because right now you can do that with C++ 17. That looks like Go. So those who like Go, I doubt they would find fault with this. It really looks like what they're used to. And they find that to be nice. So why not? You can do that. Okay, there's nothing wrong with that. So OK so far? And if you say, I want that, this is a cool feature, you're right, it's a cool feature. So C++ 17. We have compiler writers in the room. We love them when we hope for them to do a good job. I see them. This is another option. You can return optional. We're going to have an std optional in the language, like anytime now. Maybe I'm guessing some compilers, some libraries already have that. So an optional is a variable that's either has something or doesn't. It's testable as such. I think I use the right syntax because my compiler doesn't support it yet, but it essentially works like this. If you cannot do the job, you return something that is recognizably false. In this case, it's a default optional. It's wrong. Otherwise, you return an optional that contains something. Why not? And then if you look at the result, it actually looks good. I mean, you take your variable, you test it. And if the test succeeds, you check the value. It's a dual interface within a single object. It's pretty cute. It works. So yeah, there's many ways to do things without exceptions if you don't care about them. And they're all essentially equivalent in terms of costs. You could do this way too with C++ 17 because you can make sure that your optional variable only lives in the scope of the if, as long as if you want to keep the result afterwards, you let it out somehow. But if you want to encapsulate your test in your if statement, you can do that now. Cool? OK, so this is C++ 17. I actually hope for that. These features are very nice. You can do it with an expected. Expected is kind of an optional extended, but there's no standard accepted in C++17. There's a proposal on the table. The idea is you get the value or something else of a type that the caller chose. So you can have an error code, you can have many things. So the caller is essentially, this is like an optional where you can have something else than a bool. It's called that way. So it's a generalization, it's pretty cute. So in this case, I'm using an empty class as return type should a problem occur. It's a divide by zero kind of thing. And otherwise I have the result. And you can do something like that too if you want, assuming that the result is testable, which is not the case in this case, but it looks like optional code. And well, something like this. It's cute. So there's a tweak missing for the Boolean state, but not much. And you can throw. It's crazy. You can actually use this. Exceptions. If there's a problem, you throw a problem. And now, why do you throw? It's because you can't manage a problem. You don't know what the context is. You can't display something. Where would you display it? Is it a graphical display? Is it something made with text? Is the world falling apart? Is it a spaceship falling down? So you don't know. So because of that, you need to take some action, and your action is to signal the problem. You can't process it. You can't go forward. You don't have the information to do a correct job, and you don't have the information to actually do something about it. The only thing you can do is say, damn. So you don't corrupt your code. You keep it safe. You keep it OK. And you throw it. When I'm giving a class, I'm actually throwing things at people. That works. And then they take it and they throw it back. You know, it's cool because the ping pong thing is essentially what's going on for real. At some point, it ends up in somebody's hands. But if it doesn't have to, you don't process it. And you know what happens if you throw something and nobody catches? You die. But that's what some people want to do anyway. If you don't care, this is perfect. If you don't care about managing the problem, well, you have nothing to do. What you want to do is crash loudly. And you want to debug your code, fix it, and ship it without bugs. So that's actually good behavior. You're not supposed to swallow the exceptions. You're supposed to either do something about them or crash and fix the bug so that it doesn't happen again. So that's the correct thing to do. If you don't catch an exception anywhere that's been thrown somewhere in your program and your compiler notices it, the compiler can call terminate. But that's OK. We expect that. So far, so good? OK. So this is actually cute. We have the normal code. We do nothing special. It's the original interface. It's the correct behavior. It's essentially as if someone was breaking the precondition condition and dying in some cases, which is expected. And there's no try and there's no catch, which is one of the points here. So many people hate that because they say, I'm going to clutter my code with tries and catches. No, you won't. No, you won't. You won't do that. You're going to do that if you have something to do about it. What would I do here? Apart from saying, oh, damn. What can I do? I might try some user input again and again and again, maybe if that's what I really want to do, but otherwise, you know? Okay. So and of course, C++17 could look cute there because you can actually make sure that your variables live inside your if scope. That's cute. It's just because I'm really looking forward to C++17. So OK so far? So in most cases, there's no point catching. Try blocks are fast, catch blocks are slow, but you have to do something about it. If you have nothing to do, you don't do it. And if you catch, you don't necessarily have to handle the exception. But sometimes what's going on is you caught the problem, not because you want to manage it, because you're responsible for something. You have to clean up. You allocated some resources that will not be destroyed the way you wrote the code, because you're in a constructor somewhere and the constructor hasn't completed, so the destructor won't pass or something. So you have to do something. You have to close a file. You have to whatever. RAI helps, of course, in these cases. But should you be doing some raw memory management, sometimes, well, you want to catch just for a little amount of time because you want to do some cleaning up, repairing the things you've broken. And then you let it go. Let it go as is. You don't hide it. You say, I catch something and I throw a whatever. No. You let it get out the way you got it. Because you haven't managed it. So you want the ones who will actually be able to do something about it to know what occurred. If it's an SQL exception of some kind, let it be. If you're out of memory, you better know about this. Question?
You're saying you have to catch, but what if you have several levels of exceptions? Maybe you got a low-level exception, and sense to raise a higher level exception?
Well, if you do that, you're going to hide what occurred.
Yeah.
So, well, if this is your use case, there's always a use case for everything. We're in C++. There's no feature that has no use, to be honest. But it would be my default reaction, because if there's been a security problem somewhere and you're returning something of a higher level and there's no way to know the details of the security problem, you're going to have trouble managing it.
But maybe there is a security problem and you're raising a divide by zero exception.
Okay.
And maybe you want there is a security problem.
In that sense. Oh, that would be an interesting case indeed. So my friend here was saying if the lower level thing hides the details because you got a divide by zero, but you don't know why, and at some higher level, in your management of the problem, you're catching that the reason why you have a divide by zero is that there's an overall security problem. Should you raise a security problem? Yeah, you should. In general, you want to let it filter, but to be honest, there's always a reason for everything in C++, so you always use your mind. A guideline is not a replacement for thinking. Okay, thank you. Any other comment? Michael Casey would say the same thing. If you've been to his class, he would tell you, well, it's cool to be told, do this or do that, but the one thing you should not stop doing is thinking. So thank you. Okay, and if you got something and you couldn't do anything about it, you just had something to clean, well, it's in your hands, you just throw it back. I mean, somebody will catch it at some point. There's an example there that's taken from one of the classes I gave last weekend. It's tightened a bit. It's a generic array. I won't show the whole code, just some pieces of it. It's a very, very simple thing where I'm doing manual memory management. I have a T star. You see that? And if you see, look at, I have a pointer to the first element, an integer for the number of elements, and an integer for the capacity. It's very simple stuff. So there's, from the beginning to some place, you have data, and from that place on, you have, let's say, empty objects. It's a naive thing. We could do better. And there's a number of minor functions like size and capacity that just work and do what you expect. And you could see there the no except thing that says that it either won't throw, or if it throws, you're dead because you just broke the contract. There was a noise there. Yeah?
It doesn't do what I expect.
Oh, damn. Why? Did they make me mistake?
Specifically returns an element.
Because it's a mistake on my part. So I'm going to fix the slide. Thank you. I did that this morning because I wanted to have an example. So there's the cap that's supposed to be returned there. Thank you, Dietmar. But that's just a typo from my copy-paste thing. So everyone understands that it's cap? Okay, thank you. Well, thank you. I'm going to fix that. The slides aren't yet in the folder, so it's all going to stay between us, and nobody will know ever. Shh. So you can have some simple iterators. In this case, it's just pointers, just to make the code simple. Fair enough. All of those operations are no except, by the way, because if you're using your thing and somebody's returning a null pointer and doing something wrong with it, it's not your problem. And you don't have to throw something. They shouldn't be using a null pointer. It's their problem. And I put this pushback there in boldface. The reason being that it becomes interesting at this stage. It's a naive thing, okay? Because all the experts in the room will notice that memory management is very basic. The if there is checking if the container is full. Because if it's full, we need more space. The capacity is taken. And growing might throw, because we're going to allocate memory. We're going to copy objects around in this case because it's naive. And we're copying T's, and copying a T, well, it might do anything. You don't know what it is. And allocating memory could throw, possibly. It makes sense. And you might notice that there's two lines after that. There's the copying of arg to a position in the array that is now big enough to contain it. I know that. I know that because if grow failed, I'm not going to the next step. So by definition, by construction, if I go to that assignment line, I have enough memory to put the arg. Okay? And then I'm incrementing the variable, and you can see that I did these two things in 2 steps. I didn't do size enums plus plus within the brackets in the third line to make sure that the assignment, which could throw, if it throws, I'm not incrementing the number of elements. Otherwise, I will get an incoherent container, which is not seen to be a good thing in most circles. There was noise in the audience. So that's the way it's done there. And I did a naive grow in this case. It's very naive because it doesn't work, it's broken. It's all boldface, so it's not saying where it's wrong. but this is the function I'm going to look at right now. And there's so many ways this could go wrong, which is the beauty of it. The first thing that could go wrong is the new array of t there. So on that line, beautiful, I could have an allocation failure because it's too big of an array, too big of a block of memory to allocate given the resources I have at that point. And not only that, but I could have a number of exceptions because I'm constructing naively many t's in that array. At least new cap, and exactly new cap. And each of these constructors could throw because I don't know what it's doing. It's a t. It might be a string, a vector of 3 objects, or whatever. Music, database components, whatever. But if that fails, I don't care. It's not my problem. You know, if that fails, my container is still okay. My size hasn't changed. My capacity hasn't changed. My pointer, the first element, is still the same. It's not my problem. So if it fails, you know what? The error will get out and go to whomever might want to manage it, should they? That's the beauty of exceptions. It's not my problem. It becomes my problem after new, because at that point, if something happens, well, it's in my hands. I requested it, I got it. But you might be saying, well, nothing bad will happen. Well, things could happen. Well, this is not a problem. It could fail, but I don't care. This is not a problem. This won't fail. Right? Destructors with that throw, your program is already dead, so you have other problems. You won't recover from that. So that's pretty much okay. Can't do anything about it. Don't worry. This is a problem, though, because copy is making assignments of t's to t's, which is an operation I don't know nothing about, because I don't know what t is. So each of these assignments could throw. So this is where I have to protect myself, because should that thing throw something, then I'm stuck. I'm going to leak. And it's not the memory I'm going to leak that's bothering me in this case. It's the fact that each of the t objects could be handling some resources that are very precious, like credit cards. But maybe it's not precious to you, but in my life, it plays a role. So this is what I don't want to let as is should something fail. Because if something fails there, then I have a problem. Okay. So now if I had to try a block, it's becoming bigger. But that's the thing you have to think about. You know, it's the very case where there's a problem is this one. I'm putting my gloves there and being careful because if something fails, well, I have to at least clean up the memory allocated in the object I created. And that's pretty much what I can do. I can do more than that. And I don't know what's being thrown. That's why I use the cache ... thing. I use that because it could be anything. But it doesn't matter. I'm not handling the problem. I'm just catching it along the way like this, doing things as it's screaming and moving like that. And at some point, I let it go. That's perfect. I let it go when I've done my job. And somebody else will do its own. Okay, my job is done. My container is intact. I haven't leaked anything. I'm OK. So far, so good? Okay. Of course, I can do better, because I have RAII. That's so cool. So should I put my newly constructed array in a unique pointer, which becomes then responsible for the resource? Well, when I do my copy thereafter, if it fails, my container is still intact, and my resources won't leak, because the unique pointer will die an horrible death. There will be blood and fire and like legs, but the right thing is I'm not losing anything. And once the copy's been performed, the rest of it is at no risk. So I'm doing my small things, taking the pointer away from the unique pointer because it's done its job. It's held it nicely for me to let me write clean code. That code is actually very short. It's actually very clean, and it's actually very fast. And I'm not doing any try, catch, or other kind of exception handling. It's just being done on its own. There's no leak. So exception handling doesn't have to be complicated. Making any sense? Okay, good. So RAII really saves you. RAII is so cool. But you have to be careful, okay? Because I wasn't handling anything in this case, and should no one be handling anything, well, the standard says things. The standards do that. They say weird things. The more you read that thing, the more you feel strange. Thank you. So if you read this, it says, in some situations, the handling must be abandoned for less subtle errors. And then there are situations. And you're saying, well, after completing the initialization of the exception object, well, there's many things that could occur. But there's the case where the exception handling mechanism cannot find a handler. So there's no one catching the thing ever again. When the compiler finds that, terminate is called. So if this is not good for you, you're going to have to put a try catch somewhere. And there's other things there that give you the rules. If you had a no except and someone threw, or if someone threw and no one caught ever, the implementation is allowed not to clean up anything. It can just go away. So if it matters to you, you might want to put at least a try catch somewhere in your main. Just to make sure, because otherwise you're going to have a quick exit, which is probably what you wanted. But should you want the global variables and everything to be cleaned up properly, you might want to be a bit careful. But that's about it. Okay. I cut up pieces because it's a big part. So if we summarize that part at least, well, just printing a message is evil and you should be shot. No, you should be shot. You should be scolded. Terminating or asserting makes sense in some cases. You might want to just make a quick log, die, restart, that's okay. And those situations probably shouldn't happen. Just fix your code. Even in other languages. I had a talk with a guy, a C# guy last year, who told me, I never let people away in my code with exceptions here and there. I mean, when we get exceptions in debugging mode, we fix them. And we only keep them for the really exceptional cases. I mean, it doesn't matter that the language supports them, it's a bit slower. We fix the code before we ship. Yeah. And you can alter the signature. The piece there comes from a tweet that I saw pass a few months ago, where you can use macros to simplify your code if you change the signature. It's not necessarily clean or pleasant. You need discipline. You need to not miss any. It's painful. You could return rich types like pair optionals, expected, and you can throw an exception. That's it. There's a performance issue then. There are things you can const_expr away or you can use with const_expr. That's pretty cool. Terminate, exit, abort for some reason are not const_expr. Okay, so those options are out. You can, the natural version with an assert, you can actually const_expr away. That's possible. So in those cases, you could have the resolution of your division at the compile time when it's reasonable. Why not? So you could do that thing. The assert will crash if you're doing it at runtime. Things like this, you cannot const_expr away because they're writing into a pass-by-ref argument. So those strategies are out. If you want const_expr functions that have error management, this is not an option. Something that returns a pair is an option, as long as the types that you're returning in your pair fit in with the const_expr paradigm. You're okay. This code actually compiles if you use it. It works. Because it's instant bools, it's very const_expr-able, so that's an option. And of course, this is an option, but this might surprise people. It's hey, whoa, throw is dynamic. What are you doing? No, whoa, calm down. Const_expr is not always done at compile time. It's at compile time when it makes sense. When the context asks for it. In this case, well, it's going to, if you pass it, arguments not at compile time, and the denominator in this case is not null, it's not 0, well, you're going to get your computation at compile time. And if you pass it 0, you're going to get your computation at runtime, or it just won't work, depending on your preference. But it depends on the context. But you can actually do that. That's working. You can try it. Of course, this is not a plaidoyer or a plea for this small function. It's pointless, just an example. So the point is, you detect your problem in a place where you don't know, where you don't know if you can actually manage it. In this case, the context is not known to the called function, and you want to push it away. How much do exceptions or do errors pollute your normal path? Well, when there was this fight between Knuth and Dijkstra way back when I wasn't born, about gotos or no gotos. Knuth was suggesting that we keep gotos at least to push the error handling away from the normal control flow. So this type of thinking has been around for a long while now. The exceptions we're using today are a bit inspired by that, I guess. So if we look at the error handling when you're putting it in your normal code, well, this small thing that's unreadable is actual code that computes 2 plus 3 using COM on a different machine. Believe me, it works. I've been doing that for like 20 years. The thing is, there's so much error handling. It's very, very, I'm just exiting when there's a problem. Okay? There's nothing being done, essentially. There's so much error handling that you don't see the code anymore. And it's not doing much. It's creating an object, passing it getting an interface, passing it arguments, and showing the result. Pain. When I do this, the students cry blood. And all the green stuff that you see there, it's all the stuff that's pointless. Well, it's not pointless because you can't let the errors break your code. But it's all the things that you're doing away from the task you're trying to do. And if you remove it, well, it's a bit more sane. Not that much, but it's a bit more sane. At least you can actually read the characters from the room if you make an effort. But there's a number of HRs there. All the red things, they are the cases where we're getting a result that we should really be checking. All those cases change the signature of our code because we're not getting the result from the function, we're getting an error code, so we have to work around that. And there are cases where we should be doing more because right now, if we're not checking, we might fail and crash. So if we clutter everything together, you had the word soup that we had 2 or 3 slides ago. It works, but is it the easiest way to make your code debuggable and usable? I'm not sure. So there's upsides to that thing. They don't affect your interface, apart from no except, because now no except is part of the functions interfaces. Since C++ 17, if you take a function pointer, no except is part of that. They create alternative code paths for the unusual stuff, so you can focus on the real stuff, so they don't pollute the normal code path. And they separate disappointment. The word disappointment is one I love. It's from Lawrence Kroll, who went to the SG 14 meeting last year, I think, and who said, well, there's so many ways. Exceptions are not errors. It's more subtle. We need a word for all those ways to express what went wrong. And he found disappointment. Bad guy. I love it. It's very pretty. So they separate the disappointment handling from disappointment detection. And I haven't stated it so far, but they can actually be used to signal problems from constructors, for which none of the other things we've checked, apart from terminate, can help us. That's already something. I mean, because think about it. If you let your constructors fail silently, you're going to have to check your code all over the place because you have no encapsulation anymore, because you have no objects in your system. You can't enforce invariants. So your code becomes cluttered with ifs. Some people like if statements. I don't. Well, some people don't like it because the alternative code path, which is a good thing for some things, people say it makes my code hard to reason about. Where are things going? Like gotos. Yeah, they are. They have non-zero cost. I was trying this morning to put slides with numbers on them, and I didn't get around to it for a time, but I do have the numbers. Okay, what I did last year, for those who were with me, I got numbers up from small tests on, I think I used 2 compilers, or maybe 3, I'm not sure, where I checked the cost of code that handles problems with returns and code that handles problems with exceptions in a number of small situations, including stack unwinding, where you have a number of recursive calls and objects are being destroyed coming back up. Small strings, big strings, vectors of things and everything. And the numbers were telling us, in the micro benchmarks, that we were suboptimal with the exception handling cases, except in a weird case with big strings on Microsoft's implementation, a very specific one. And I wouldn't bet my life on that special case because I've been spending a part of my week with the Microsoft people talking about the string cases, and they're fixing them right now. So there was something very weird in the implementation that is going to be okay probably in the next release. So there were some very strange things that they are discovering because they're playing with string view right now and they're reviewing their strings saying, oh boy, we did that. So it's going to work better, I think. It's going to be more stable. But the numbers exist, so I'll publish them. As far as this morning, because I was doing the numbers this morning before I came in, exceptions are still being outperformed by return codes in almost all cases. I checked Clang on Windows, MSVC, and GCC, but to be honest, some of them are remote things, so I don't have the machine specs. There's variation in the quality of the results, but internally for each compiler, it's coherent. That's the thing. So there's still work to do. It doesn't mean it's bad. It means we might be doing things better. In Ulu, this summer, in June, I had a chat with the GCP people, and they were telling me that one of the reasons that their implementation of exceptions is slow is that it was written for machines that do not exist anymore. They were written for the machines of architectures from maybe 10 or something years ago. So it probably needs more love today to be more in tune with the machines we have today. They're not applying the strategies they would apply if they were redoing it actually. So we might see a change in a year or two. Okay, let's hope. It's not bad, it could be better. So there, when you're at the boundaries of code that handles exceptions and doesn't, Lisa Lippincott, who's in the room right now, has a nice technique where you can make your code with errors converge on one side and exceptions converge on the other side, and you can bridge between the two. Stéphane Dutoit did the same thing a few years ago, 2 years. He called them hourglass functions. So there are ways to handle those situations where you're at the corner cases between one world and the other. It's well documented. Because that's one of the problems. Some people don't like exceptions because they have a code base that has no exception handling, and they're saying, what happens if we throw? I mean, there's so much code out there. We won't name them, but there's big companies. We can understand that. So the micro benchmarks from last year, they were done with what you can see there, and a number of you. The tests that I ran were these. So generating a number of integers from -100 to -100 plus 5 billion or something. I shuffled them, and then I played around. I went through all of them, and every time I detected a negative number, there were 100 over the bunch. I either returned an error in one case or threw something in the other case. So the thing is, it happens not frequently, not as a bunch. It's spread out, so you can count it. I tried that. I tried a function that's been called recursively many times at various depths, 1, 2, 3, 4, 5, up to 10. The reason I stopped to 10, I used to go to 32, is that the online compilers, they only give you small time slices. And the tests were too long, so they crashed after 10. So I reduced it to 10, but it doesn't really matter, to be honest, because the numbers were very stable. I was getting like very straight curves in all cases, so it would have just made more numbers, but not better curves. So the thing is, I'm going down, and then at some point, decide, oh, it's going wrong. Ooh. So I'm returning. So there's a lot of ifs and returns in one case. I'm just throwing way back up on the other side. I was hoping doing that the just throw there and catch at the very end would do a good job, because stack unwinding is what it's built for, but sadly enough, that's not the results that I'm getting. So, but you'll be able to play with the code and numbers if you want. I'll add the URL in the slides today when I have the chance, and you can pick the PDF and play with it. There will be a folder with the numbers I got and the code I used. Since the strings are a special case, and I could see that the numbers were weird on one compiler, I did the same thing with a vector of chars, or a vector of chars, I think, and I got similar curves. Okay, so the compilers within themselves were behaving in a coherent manner. They could be faster or slower, but there was no case where the exceptions were outperforming the return codes, sadly. Last year, I also had a suggestion by Sean Parent, who said, the guy from Adobe, who's very bright, who told me you should try cases where nothing happens. Because maybe the compilers will be smart enough to realize. Because that's one thing, if you never throw, I mean, if the compiler sees that, maybe it can optimize everything away. And if you're putting the ifs, you're still going to do the ifs. But the fact that you're throwing and no one's, you're making try blocks, but no one's ever throwing, maybe it's detectable. So I tried it. I tried two. I tried one with redundant checks, which means that I'm still trying and I'm still doing the ifs and everything, but I'm never throwing or returning an error ever again. Cool. And another one where I'm not checking. No ifs on one side, no try on the other side, nothing. And the numbers were very stable again, and I was hoping for better numbers. They're not miraculous, sadly. So there's work to be done. Okay. The issue of performance is real. It's not major, but it's real. So it can be annoying for embedded systems. People who are very tight on memory or on speed or something. The size issue, I didn't measure it this morning for lack of time. The numbers I got last year were about a 3% difference when I added exceptions or removed it from, I'm going to go to the questions in a few seconds. So the size increase was slight, but existed. Now 3% is that big or not, it depends on your application domain. We had a discussion in June again for other features where one of the compiler writers stated that he had measured a 3% cost for doing what the proposal suggested. And some people said, well, 3% is nothing. And he said, no, it's big, because that depends on your perspective. Okay? So the games people, the embedded systems people, the high-frequency trading people, 3%, it might annoy them. Okay, so it's not because it's not in your domain that 3% happens to be important, that it's in everybody's domain, and C++ is a big world. So that's the reason why, even though it's a very good mechanism, it does a job, we, one, have to work on it a bit, because it lacks love. And two, there's legitimate reasons for people to be uncomfortable with it, on a technical from a technical standpoint at least. Okay. So there, and that's the other test I was talking about. That's pretty much it. I wanted to make a resume of all this, but I didn't get around, so I just made a discussion with you guys. So a few things before I take the questions. I've heard a few times, even this week, because I've been here since Saturday, well, the standard library throws. Well, it throws very rarely. It throws in vector at. It throws when your code throws, because it cleans up and rethrows. It doesn't throw much by itself. So a standard library is not a big exception user. It's just making sure it's not getting corrupted. The new exception guarantees, but it's not someone that throws something that throws exceptions for you. It doesn't do that. Mostly the exceptions come from new. And some people are saying that maybe new should just die if bad luck is being thrown, just die. But there's a talk this afternoon by a guy named Zubkov. I would like to go there, I won't be able, who says that he has ways of ending bad luck. So there may be interesting things to do with that. And there's a few things, I won't have the time, that are cute. I'll put the code in the folder if you're interested. I know that Boost Graph throws when it finds something instead of failing, because graph searches are so complex that finding something is exceptional. And I really like that, because it's not an error, it's an exception. So it's the normal case is not finding something. Okay? So I agree with everyone who says you should keep exceptions for errors. Well, yeah, in most cases, but again, C++ is a big world. And the Kazuneri there, from what I know, because I've never met him, is an accountant. Nice, eh? But he had a problem. He wanted to do type erasure on a pointer and make sure that he could get the pointer out, but that or one of its parents' classes. He wanted to do some polymorphic things with it. And the type erasure techniques that we had went for the exact type. And he found a trick with exceptions to be able to get either the type is stored in the pointer or any one of its base classes. It's a nice trick. So I'll put the link in the slides before I put them on. You can go check. It's a very nice trick. And you can, if you're very dirty, you can throw a lambda that casts to a function pointer and that tells you how to handle the errors. But don't do that. But there's many interesting things you can do with exceptions if you're creative. It's a whole world. Now, if you're too creative, you're going to lose your job. So you don't. Yeah. So that's pretty much it. So on the slides after that, there's a trick. But since the time is running and there are questions, I'll take the questions and put the slides on for you. Is that okay, guys? Thank you. So you had a question?
Yeah, I was just wondering, did you test it with functions that were marked as no except and did not throw any exceptions, like a return?
It's a good point. I don't remember the code by heart because I was rechecking it fast this morning, but it's a good point. I'll try to think about it and add another test case should I have forgotten to do it. Thank you. Jonathan.
Just like the code size of exceptions will find if you use a profile guided optimizer, all that code is stuck. It's stuck together, and it's cold. And unless you hit an add exception or you hit a catch, it's never actually touched. So the code size itself is not really a measure of a change in performance.
You're right. The reason I was mentioning this is because it's one of the criticisms we hear. So on SG14, at first, the discussions were not based on numbers. That's the real reason why I started doing this was that discussing performance without numbers is very annoying. So the benchmarks in terms of size were very simple. I just compiled the same code with very different, essentially the same settings, and I just checked the difference. There's a guy whose name escapes me. I think his name is David, who's compiled Clang with and without exceptions just to check, and who's done I/O stuff, and who's found that depending on the context, if you do a lot of I/O, sometimes the exceptions perform much better. So it's not the end all of it. But, generally speaking, naive code, we have some work to do. That's what.
We tried turning on exceptions in our compiler, and no way.
I can understand that. Yeah.
If you should have to do an answer as a general verdict about about exception and performance, are you pros or cons?
I use it. And I work with people who really need speed. So I personally use it. I don't use it everywhere. Okay, I use it in constructors. Since I write generic code, I'm careful. So I try not to leak resources, but RAI does most of the job for you. So I use that. I wouldn't use it in tight loop ever, unless I have a really, really good reason for that, because it shows too much on those places. But there's a number of places where it's fine. I wouldn't use it for I/O. In C++, errors in I/O are too common to be called exceptional, I think. They happen too often. So I know that some languages do that. That's not where I would put it. But as far as keeping a code coherent, safe, for those places, constructors, and other places that are not tight loops, I wouldn't hesitate. You don't have to optimize everything in your code. You have to optimize the hot stuff. So I would localize them. And if I have pieces of code that really need it and the rest doesn't, well, you can write a DLL or an SO and localize them together and make sure that on the boundaries, should they escape, you have things to do. There's some people who have been asking us recently on the mailing lists if we should catch exceptions from other languages. I think it's just pure evil. I would use Lippin constructions for that and hourglasses. Yeah?
So two things that I would imagine if you're trying to get performance numbers between using if statements versus using exceptions would be, or even just code size would be a generally hard problem because like if you look at the Linux kernel, because they're using C, they're stuck with if statements, but they wrap everything in branch prediction.
Yep.
So, and even if you don't do that, normally the compiler can do it for you. So to try to measure what would the impact be of a bunch of if statements versus an exception would be incredibly difficult because generally speaking, branch prediction should just make the problem go away.
Well, it doesn't, but that's the theory.
And then from a code size perspective, if you got rid of all the if statements, right, you would be removing seemingly a lot of code by using exceptions, but then the exceptions add all of the basically exception logic that's needed to do all the lookups for how to do the stack unwinding. Mm-hmm. So yeah, you might be reducing code size in the actual code that you're writing, but what gets compiled ends up being relatively large due to the fact that it has to have a lot of lookup data. Well,
it can be. The question is, are we doing the right thing? In fact, so far, my feeling is we have a QI thing. I think we can. I'm not sure we'll be able to reduce the code size below the if statement level, but we can get close, and we're not close enough. That's more the thing that's annoying right now. We don't have a strong statement to say we're close enough. You should really try it.
So we're using it. So I actually wrote a custom unwinder for our hypervisor. We're using it quite a lot because it's nice for handling a lot of different types of problems we see. But yeah, when we wrote that code, it was very obvious that there's definitely these weird problems that you're going to have. So I would agree with the statement that it's good in some scenarios and not good in others. You have to use your brain to figure that out.
Oh, damn brains!
The second thing I looked at the scope guard work that was presented a couple of years ago with respect to dealing with state.
Well,
transactional.
Specifically the scope guard, no, but RAI I've been using now. It works magic.
It's an interesting discussion that we had on the core guidelines GitHub page with respect to how to deal with on success or on failure with respect to RAI. Because I think there's an interesting concept there where GSL finally can be used, except for the fact that it's always executed. So in the case where you have exceptions, what do you do? And so there's an interesting discussion of building essentially something similar to scope guard, but with RAI and more C++ 11, 14 type features.
If that becomes standard, it's going to change the way we program, so it's going to need some more thought indeed.
Yeah,
but
if you have state problems and you have exceptions in the mix, there's a problem there. How do you reverse your state if needed? I'm surprised that there's not more discussions on exceptions and dealing with transactions. How do you brought up the issue of I do that copy, but what if only part of the copy occurs? And how do you roll those changes back?
Maybe you'd like, we're going to have to stop because I'm getting messages from the backend. Maybe you'd like to check what the transactional memory group is doing too, because it's a real problem for them, of course, and they have a number of techniques and ways to mark the code to know what you do should something fails in the middle of a transaction, a listed transaction and everything. Do you commit? Do you roll back? Do you fail? Do you... and they've given it a lot of thought. Brett Hall, who's very often, and who has a transactional memory commercial product, probably has thought about that too. That'd be interesting. Yep.
Also, another person who's also big with transactional memory is Michael Wong.
Yeah, he's the manager, the chairman of that committee. But there's a number of people involved in there that are here in the room, but not in the room, but in the building right now. Anything else? Yep.
So a lot of compilers have intrinsics to tell the compiler that an if statement is unlikely to be taken.
Yeah.
Would it make sense that if the if statement has a throw in it, you should then tell it that because an exception is an exceptional situation, it's unlikely to be taken?
It's a good question. The SG14 group right now is working on something with that respect. Jonathan was talking about link time optimization today. The relation of your code to what's hot and what's not sometimes is not the same from the perspective of the compiler and from the perspective of the programmer. I've heard people saying, well, I want the hot path sometimes to be seen as the catch because even though it's not going to occur often, it's when it occurs that I'm really in a hurry and I have to do something. So it's not an either-or thing. It's tricky a bit. So these guys are working on, they're trying to find ways to use standard attributes because right now we have a number of non-standard ways of doing this. There's the GCC way, the Clang way. So we're looking for ways to express the intent for the compiler to do the right thing, and it's exceedingly difficult. A number of bright people who have real problems are trying to find the right words and the right semantics right now for an actual proposal eventually. So it is an interesting case. It's not an automatic thing. It's something that requires thought. So I'm hoping that these works will give us guidance as to what we should let the programmer do and what kind of leeway we should leave the compilers, because the needs of performance critical code are not always as evident as we would think. It's a very interesting thing. I'm not in that conversation much. I'm reading it and I'm having a lot of fun. There were hands. Thank you so much.